Okay, so welcome everyone. Welcome prospective students. Pleasure to be talking to you today. We haven't chatted yet, but we'll get opportunity to do that after this talk and tomorrow as well. So today I'll tell you about some work that has been ongoing for many years now, and it's involved many people, former students that are still collaborating with me on this, and current students as well. And I'll try to highlight that as we go through this. And so the whole point here is that I'm going to be telling you about work we've been doing on estimating monotone function. Seems simple enough to state that as a topic of research, but there's interesting intricacies that come up in that context. And not to say that, I endorse what Kevin said, that this is meant to represent the whole, a big chunk of the department, but I did select this topic because it does touch upon I think the entire spectrum of statistics, from theory to methodology to meaningful and truly motivating applications. So hopefully there's a bit for everyone in this. And yeah, so I want to start because I have this background that I have here that I've been using recently, a beautiful picture of the campus and of the city. And normally that's it. It's in watermark, so it doesn't show very much. But for you, who will be considering choices, okay, in the time to come, I want to show you the actual picture without the watermark. And this is, and you can actually see here, right here is the building we're in, the magical building that we're in. And this is the magical campus that we're on. And this is the magical city that we're in a magical state. So truly, and I say this sincerely, I didn't know what to expect when I joined UW. I had really never been to Seattle except for a short visit. And it's a magical place, truly. And I can't imagine being anywhere else. So this is the amazing setting in which we get to do the important work that we do. And that's important because, yes, I mean, the academics are critical, and, I can tell you on and on about how amazing things are here with respect to that, but where you choose to go will also be the city you're in, right? And so that's also important. That's important to consider as you make your decision. Okay, so let's get to the actual science. So the setting is pretty broad. So in many applications, we may be interested in learning about a curve. It does say what curve? A curve, some curve, right? And we may have background knowledge, a priori knowledge about what this curve might look like. Often that's encoded in terms of shape constraints. What shape might we know this curve to be a priori? And these shape constraints may either be justified scientifically, background science we have, and I'll give you examples, or actually simply guaranteed by the rules of probability. Again, I'll give you an example of what I mean by this. And a common shape constraint that does occur in practice is monotonicity. So it's often the case that you're trying to learn a curve that you know is monotone. Again, either because of science or because of rules of probability. So here are two cartoon examples. And they're cartoon because the curves are not real, but these are actually coming from real applications that I've been involved in. Okay, so the first one here is a curve of the 6-month risk of an infection, say COVID infection, as a function of antibody levels. Okay, so baseline antibody levels. This is the kind of curve that we often produce in the context of vaccine trials when we're studying the mechanism for which vaccines are acting. And we might know that, I'm going to remove my mask actually. We might know that the greater the level of antibodies that you have, the more potential protection you have. Right? So this curve is monotone. And so it never goes up, it could potentially go down. And then here, instead, we're looking at, let's say, an infection. You have an infection, say, with SARS-CoV-2, and you're looking at the time until resolution of symptoms. Okay? And that is really just a distribution function of the time until symptom resolution. So that is obviously monotone by probability. Okay? So this is another application. In fact, this is the application I'll be focusing on in this talk, later in this talk. So these are examples of monotone curves that we may be interested in estimating. So now you might ask, okay, well, what do you do with this monotonicity? How does it help you? Okay, so how can we leverage monotonicity? And here it's useful to distinguish between two cases. The first case is one in which the curve that you're trying to estimate is one that you can already estimate pretty well without leveraging that monotonicity. So Pura say that points on this curve can be estimated at root and weight. Okay, so for those of you who've taken the 580s, the parameter is pathwise differentiable. Okay, so it is a global quote unquote parameter, one that really the entire data set is helpful for estimating every point on the curve. So, and in those contexts, we already have templates for deriving really good estimator that are, root and consistent, asymptotically normal, and even efficient if we're seeking to maximize efficiency. But many of these methods will tell you how to construct a good estimator for every point on the curve, right? And those estimators may not necessarily enforce the monotonicity, right? So you may get a curve that's supposed to be monotone, but it's bouncing around. In that case, we can monotonize the resulting estimator. So we get an initial estimator, we basically fix it by making it monotone, and we can show that doing this will actually reduce the estimation error of the estimator. So we'll get a slightly better estimate. But it's mostly in small samples that we'll get those benefits. That as sample size grows, the benefit of doing that actually washes away, and you in fact get the same sort of asymptotic theory for those estimators. So the gains are real, but they're finite sample, and they vanish eventually. Okay, so that's the first case. It's an important case, but it's not the case I'll be focusing on today, because in some sense, it's the easier case. The second case is one in which the curve itself, the points on this curve, cannot be estimated at root and root. So now we're talking about much more local parameters. So if you want to contrast between these two in your head based on very simple examples, think about estimating a density function versus a CDF when you have IID data from a distribution. The CDF is something we can estimate at root and rate. The density in a non-parametric model is not. Okay, it's a much harder, much more local problem. So in this more local setup, case 2, we generally don't have templates for constructing estimators that give us the ability to draw inference. What do I mean by that? Constructing valid confidence intervals, getting tests, okay? That in case 1 happens very simply, but in case 2 it doesn't, okay? And this is where monotonicity could make a big difference. If you know that you have monotonicity a priori, you can actually leverage that to construct principled estimators that actually do give you the ability to make inference, okay? And that's a really big win. So that's really what I'm focusing on today, case number 2. Okay, so what's the goal? This is a literature that goes back to the 50s, long, long time ago. So more than 70 years of precedence here. So this is not going to be a full review, but I'll give you sort of tidbits of the history to give you a sense of how we got to where we are today. Okay, so I'll start with just some early historical precedents, then tell you about this unification framework that we developed several years ago for inference on monotone functions. And finally, I'll illustrate the use of this framework using an application from infectious diseases, a real application. It was not, we weren't fetching for it. It sort of fell in our lap, and it was exactly requiring these kinds of tools. Okay, so back to basics, back to the 50s, literally. Okay, so a simple problem where you may encounter a monotone function is one in which you get to see pairs on individuals. You see an outcome Y, and you see an exposure A that lives in 0, 1. And just for simplicity. And we care about estimating the mean of Y given A, the regression function, mean regression, mean of Y given A, as simple as that. And the knowledge that I'm telling you you have is that that function is monotone. Say for completeness, non-decreasing. We know this for whatever reason. Okay, maybe just scientific background. What do we do? Okay, what do we do with that? So if we have observation and observations from this underlying distribution, we might say, okay, let's write down sort of the least squares, an empirical squared error of residuals. Okay, so this is what I'm writing right here. So I'm taking a candidate regression function R tilde, computing the residual yi minus R tilde ai, squaring that, taking the sum or the average, same, and then minimizing this criteria. So this is doing empirical least squares. Okay, something you've surely seen before in one form or another. And we're going to want to minimize this over the class of candidate regression functions that are monotone, because that's the knowledge we have, okay? And this is not a trivial problem to begin with, because this optimization that you're doing is actually over a function class that is infinite dimensional, not just infinitely many elements, infinite dimensional, so it's uncountable. All the monotone functions, right? And so, so it's not a given that this problem has a solution or a unique solution or a well-behaved solution. But it turns out that this was studied, again, a long, long time ago, and people showed that indeed this problem has a solution. It has many solutions, but all the solutions agree in their values on the observed exposure values A1, A2 to AN. And that sort of makes sense, right? Because if you look at this criterion, it really only cares about R tilde, the candidate, through its values at the observed exposure values, right? So anything else, we can change things around, but that won't change the criteria as long as we respect monotonicity. So there is a unique solution to this, at least over the observed exposure values. Okay, great. Now, how do we find this? Or how do we find one solution, one well-behaved solution? So that is, again, something that was done in the 50s. People came up with an algorithm called the pooled adjacent violator algorithm, which is a bit of a mouthful, but it actually tells you exactly what you should be doing, pooling adjacent violators. So we'll look at that through a toy example. And this algorithm gives you one particular solution of this problem, and it gives you the solution that is a right continuous step function, which jumps only at the observed exposure values, okay? So basically, I'm going to say in between the points that are observed, the A's that are observed, where I can potentially jump, I'm going to make it flat, and I'll make it right continuous. And if you do that, then the solution is unique. So here's a generated data set with a true regression function, just linear in this case. We don't know it. Okay, so this is where it was simulated from. And the pooled adjacent violator tells us, walk from left to right, okay, go from one point to the next. And whenever you see a violation of the monotonicity that you know to be true, replace the violators, the adjacent violators, by their average. Okay, so we're going to walk through this. So right here, the first 2 points, no violation, because now I know a priori that this curve ought to be non-decreasing. Okay, so I'm going to start walking from left to right and see where I have violations. So no violations here, so I'm going to leave these intact. Okay, so first 2 points are, I'm skipping ahead. So the first point stays here, but there's no violation. But here there's a violation, so I'm going to replace these two by their average. Okay, so here we are, the new points. Now I go to the next point. Here to here, is there a violation? Nope, no violation. But the next one, there is a violation. So I will replace these 2 points right here by their average. Okay, right here. Now, what about the next point right here? There is a violation, and the violation involves even this point, the previous one. So I'm now going to pool all 3 of these. Okay, so I'm going to average them and replace them by their common average. Okay. Next step here, no violation right here. We're going up, but the last one has a violation, so we will average that. Okay, that's the pool adjacent violator. And then we can build our step function out of these points. Okay. So this is exactly what the pooled adjacent violator algorithm tells us to do. So pretty simple to see. Now, what do we know about this particular estimator? This is what we usually refer to as the isotonic regression estimator. So again, people have studied this a long time ago. One reason why people really like this is that this is a non-parametric regression technique that actually doesn't have any tuning parameters. Okay, so in non-parametric models, we usually do have tuning parameters because the function class over which we're optimizing is complex, so we may need to do some penalization and so on. But it turns out that this is an infinite dimensional class, the monotone functions, that is small enough that you actually don't need regularization. So there's no tuning parameter, and that makes a lot of people very happy because you don't have to go through a difficult process of deciding what the value for that tuning parameter will be, and presumably the analysis of such an estimator is also a bit easier. So, so that's one property. Another one is invariance to transformations of the exposure. So if I run an isotonic regression on the A's I see, and someone else measured the same A's but using a different instrument that maybe rescales the values and runs an isotonic regression on those transformed A's, and then I take that output and I back transform using the mapping between my exposure and their measurement, I will get back the same thing. Okay, so it turns out that there is this nice invariance, and that's because if you think about the construction, the algorithm really doesn't care about the values of the exposures. It only cares about their ordering, their ranking. Okay, and so that's why we have this nice invariance. Statistical property that's of course of interest, consistency, and in fact uniform consistency over subintervals, as long as we're staying away from the edge. So in all these problems I'll talk about today, the edges are an issue. Okay, so we often have inconsistency at the edge. So don't try to go too close to the edge. But as long as we stay within the interior, we actually have uniform consistency under some conditions. And under, again, some other regularity conditions, we can actually show that we have distributional theory, asymptotic distributional theory. And why do we care about that? Because we don't just care for point estimators, we care for confidence intervals, we care for tests, right? That's what we provide as statisticians, uncertainty quantification. And we can do it with this kind of procedure, right? So what does the asymptotic look like in the simplest vanilla case? I'm showing, there are more complicated settings, but this is a nice one to discuss. Basically, what this is saying is like, look, if you're focusing on one point, I can tell you that the estimator minus the truth times a scaling factor. Now, you may be used to seeing as a scaling factor root n. That's the more common one in standard root n prompts. But here, we're estimating a local quantity, a regression function. We don't expect root n unless we've made very strong assumptions, okay? So the rate here we get is actually cube root, a slower rate. And we converge in distribution to some distribution, some non-degenerate distribution. What is that distribution? It's a bit weird, slightly weird, okay? So it is what we call scaled Chernoff distribution, okay? So this is the scaling factor, so it's a constant. And this Z right here is a standard Chernoff random variable, okay? What the hell is that? We'll talk about it in just a second, okay? But it's some distribution. And if you stare at the constants that appear inside, or the elements inside this constant right here, you see things like the derivative of the regression function, the variability of the y's at that a, the density function of the a's. And if you stare at this long enough, you'll see that it sort of makes sense that all these things are there. And whether they're in the numerator or denominator, they reflect the difficulty of the underlying problem. Okay, so I'm not going to go through that just in the interest of time, but it should sort of make sense. Yeah, yeah. One point at a time. Yes.
So there's no assumption that's
Yes, there are some conditions. Like we'll want to have some smoothness at that point, derivative, right? I mean, the derivative appears in here. So there's a bit of regularity to be able to get this, right? And we don't want the curve to be flat at that point, because then, depending on the degree of flatness, the asymptotics change. So this is why I said this is sort of the plain vanilla setting, but the theory is much more complex. And you get different rates depending on, again, if it were flat, we'd get backward n, and there's everything in between as well. So there's a whole, complicated theory behind this, yeah. So, okay, what about this Chernoff? We didn't really talk about this Chernoff. What the hell is Chernoff? So the Chernoff distribution comes up in some weird way. So it is actually defined as the distribution of the maximizer of a particular Gaussian process that's been drifted. Okay, so what is that precisely? So if W here is a two-sided Brownian motion process that's pinned at the origin, details don't matter. Okay, so this is not critical for this. So we have a Brownian motion. We're going to subtract off this quadratic term. So it's a parabolic drift. So now this here is a random function. For different x's, you get a different random variable. And now we can ask, where is the maximizer of this? Okay, and that is itself a random variable. The distribution of that random variable is what defines a standard Chernoff. Okay, it's not important. It is what it is, and it looks weird, but it comes up when you start to study these kinds of sort of monotone estimators. It comes up naturally why this would be the case, but it's not apparent right now, and it's not easy to explain. So okay, so we have a Chernoff distribution. I'm showing you here the density function in black of the Chernoff distribution, but I'm also showing you on top of that a particular normal distribution that is very, very similar. Okay, so yes, it's a different distribution. It's not normal, but it's pretty close. And most importantly, it's been super well characterized in the literature. Okay, many papers have studied the Chernoff distribution, including by our very own John Wellner, Professor Emeritus here, who is one of the biggest figures in this whole area of shape constraints and monotone function estimation. So he's done so much amazing work in this area, and this is just one out of many, many papers that he has studying fundamental features of these kinds of prompts. Okay, so Chernoff is what it is, right? We don't have to be anxious about it. We can deal with that. Okay, so that's the first historical precedent that I'm showing you. Regression, a univariate regression function that you know to be monotone. How do we do it? Okay, pull adjacent violator. That's what we're doing. It has nice statistical properties and so on. Now I want to show you another sort of not contemporary for us, but contemporary for isotonic regression, a problem that arose around the same time that is also about a monotone function that we would like to estimate. And the solution in that problem will actually give us the direction in which to generalize all of this. Okay, and then we'll loop back to isotonic regression. So there's a purpose I'm going in this order. So now the problem is, I don't get to see A's, I just get to see Y's. Okay, I see Y's on individuals. And what I know a priori is that the distribution of Y has a Lebesgue density that is known to be monotone. Okay, and here I'm saying non-increasing. It doesn't matter the direction, increasing, decreasing, as long as you know it, then everything I'm describing here has sort of an analog. So I am in the business here of estimating a Lebesgue density that is non-increasing over, say, 0 infinity. So how would we proceed? Well, we have data, y1 to yn, coming from this distribution. We can write down a likelihood. Okay, we can write down a likelihood and try to optimize that criteria. Okay, so I'm writing for you here the log likelihood, and F tilde is just a candidate density function, and it has to be monotone, in particular non-increasing over 0 infinity. Okay, and so now we can say, well, which F tilde maximizes this? And we do this. Again, it's an infinite dimensional optimization problem. It's not a given that there's a solution, that there's a unique solution, or that if there is a solution, that it actually behaves well. But there is a solution. There's a unique solution to this one. And it has a name, a special name called the Grenander estimator, in honor of the person who discovered this, Ulf Grenander, in the 50s. Okay? We're still in the 50s. And later on, various authors studied this estimator and established large sample results that look very similar to everything I've described to you for isotonic regression. Okay, there's a general story here. So these are elements of a general story that we'd like to see emerge. Okay, so now how do we actually compute the Grenander estimator? So that's where, I want you to pay attention, because this is where hopefully we'll see a generalization that emerges that will allow us to unify these problems together. Okay, so there's a really nice, you can write it algorithmically how to do this, but there's a really nice visual construction that I think will give you the gist of what's going on. So here's again a mock data set that I generated from a particular, I think it was an exponential density. Density is right here. Okay? The gray dotted line, that's an exponential density. I generate a small sample, and then I said, okay, this is the way to think about Grenander's estimator. Densities are hard to estimate, right? We don't like to think about densities. Let's focus on the CDF, distribution function. So much easier as a problem, right? So why don't we start there and maybe make our way back to densities eventually, okay? So if I say you want to estimate a distribution function, what would you do? Most likely you'd say, well, I can use the empirical distribution function as a natural estimator. Okay, let's start there. So this is the empirical distribution function based on this toy sample from an exponential. Now, we have not at this point used the fact that we know something. We know that the density is, what did we say here? Decreasing, non-increasing, decreasing, okay? We haven't used this fact yet. What does the fact that the density is non-increasing tell us about the CDF? It tells us the CDF has to be concave, right? Because the derivative of the CDF is the density, right? If that thing is decreasing, then it means that the CDF is concave. And the empirical CDF, even though the true CDF might be concave, the empirical CDF doesn't use that knowledge, right? So in practice, it may fail to be concave, okay? So can we use this information to improve our estimate? Okay. So here we have the empirical CDF, and now we're going to say, gosh, in general, it's not concave. Can we find something close to the empirical CDF that is concave? Okay. And there's many ways to do this, but one way to do it is to construct the least concave majorant. Let's process those words. Least concave majorant. So least concave majorant is the function that sits above the empirical CDF that is as close as possible and still concave. Okay, and that's this blue curve right here. Okay, the blue curve right here is the least concave majorant. And the way you can imagine finding this in practice is take a string, okay, and come down from above on top of the empirical CDF. And when you can't move anymore, you've actually gotten the least concave majorant. Okay, so that's the blue curve you see right here. Okay, so now we have something that's really close to a good estimator, the empirical CDF, but actually is concave. And a really nice benefit that we get as well is that this estimator actually has Lebesgue density. The empirical CDF does not, point masses, but the least concave majorant does. Okay, it's a piecewise linear function. Its derivative is a step function. Okay, and we can take the derivative of this blue curve and we get back this red curve right here. And lo and behold, that is Grenander's estimate. Okay, so it has a really nice natural construct. Okay, so what? What do we do with this? Okay, any thoughts? What do we do with this? This is for a density function. But now we want to move towards more complicated problems. So I give you an arbitrary function, little theta, that's monotone. Right? What do you do with that? Can you use this idea more generally? Okay. So the idea here is to say, okay, if I give you a function, little theta, that I know is non-increasing on some interval 0 tau, you're going to construct a primitive function. The primitive is just the antiderivative. Okay. So for the density, you get back the CDF. Okay. Why do we do this? In the process of integrating, often what will happen is that you move from a parameter that's very local, like the density, to a parameter that is global, like the CDF, something that can be estimated very well within range, okay? For which we have tools for constructing good estimators. That's the key, right? Okay, so we define this primitive by integration, and now we say, find me your best estimator of that primitive function. Okay, do that for me. When you give it to me, I'm going to plot it, and I'm going to compute the least concave majorant, just like I did in the previous case. Take that string, come from above, find this piecewise linear function, take a derivative, you get back an estimator of the original curve. Okay, so this is general strategy that can be used in arbitrary problems. Okay, as long as this is very doable in cases where doing this integration step indeed recovers a parameter that is estimable at within range. What happens when that's not the case? Well, we can talk about it later if you're interested. So, so that is a general class of procedure, and that's been called Grenander type estimation because it's sort of like the Grenander estimate, Grenander type. And this is old. This is going back to the 80s, and people studied or obtained results for this class of procedures. And so, in particular, Piet Groeneboom is one actually of the biggest contributors to this literature on shape constraints and in particular on monotone functions. And he established a big theory that covers procedures that look like this. Okay. And again, what powers the idea? It's very simple. What powers the idea is that if theta, little theta, is decreasing, then the primitive, the integrated version, is concave. Okay, and that's why we can do this. And I'm highlighting this as a fact because we're now going to generalize this a tiny bit. Why do we need any generalization beyond this point right here? Is this not enough? Can we stop here? We could, right? But I'll tell you about work we did to generalize this, and it was purposeful. So because if I ask you the question now, isotonic regression, the thing you started with at the beginning, it had a very different solution. The pooled adjacent violator algorithm gave us isotonic regression. Can we view it as an example of a Grenander type estimator? Turns out the answer is no, but. No, but. Close. Close, but not quite. And that's really what, in some sense, made us think, gosh, there should be something else here. There should be something more general that is able to unify these different procedures that have been developed in the literature for tackling different problems one at a time. Okay? And so it's a little twist on Grenander type estimation that actually ends up giving us quite a bit of extra juice. So what is that trick? So this is work that was actually done by Ted Wessling as part of his dissertation. So he worked with me here. He was doing the stat department. And this is a moment to highlight to you, if you come to UW, you get to work with whoever you want. And there's a lot of us in different departments, right? In the stat department, here in biostats, elsewhere on campus, lots of friends and colleagues at the Hutch, at Kaiser Permanente, and throughout, okay? We're a big community of individuals who are passionate, who are collegial, friendly. We're friends with each other, and we work together. So there really aren't boundaries between these different groups. And that's, I think, a big strength. It's not a given. It's not like this everywhere. And so Ted was in stats, but he worked with me. We have many students in biostats that work with faculty in stats. That's normal. There's no big deal. So, and Ted is now a faculty member at UMass Amherst. So what did he do? One of the pieces of his dissertation was saying, well, when we construct the primitive function, maybe we could add a little twist, which is that instead of integrating the original function theta u du, just a straight Lebesgue integral, maybe we want to allow some kind of domain transformation function. Okay, so phi right here, capital Phi, is a given increasing function. And we're going to use that when defining a primitive. So we'll call it the transform primitive. Okay. And I'll tell you in a second why that matters. Okay, but we can do that. We can consider that, get a different kind of primitive. So now, what about fact one that powered the whole procedure for Bernoulli type estimation? Do we have an equivalent? And yes, we do. Otherwise, we wouldn't be talking about this right now. So if little theta is a decreasing function, the function you care about, and capital Phi, this domain transformation, is increasing, then you can show that actually the composition, so it's a bit harder to state than before, but the composition between this transform primitive right here and the inverse of this domain transformation function Phi, okay, so it's a composition of two functions, that thing is concave. Okay, so you can show it, it's just one line to do it, it's not a big deal. But it's a fact that now we can perhaps leverage to come up with a procedure that looks like what we've been doing so far, okay? So what is the algorithm that then is sort of suggested by all of this? Well, the first step is always to estimate the various pieces in this primitive, this primitive function. So gamma is now the new primitive we have, so give me a good estimator for gamma. And this is where you would use, so for students here, the UW students, you would use the biased machine learning techniques, things that you learn in the 580s, 583, to construct really good estimator for that parameter. Okay, there's a template to follow in order to do that. Okay, similarly for phi, this transformation function is generally going to be also something that you can estimate really well using templates, existing templates. So do that first step. Okay, get me those estimators of these two functions. Then once I have that, I'm going to consider, so I know that this function right here, this composition is concave. So let me find the empirical version of that thing. Okay, so I'm just going to replace each of these by an estimate. Okay, so I'm going to use gamma n, and I use phi n instead of phi. In general, I didn't specify this, but the domain transformation function is often itself unknown. It's indexed by the unknown distribution from which we're sampling. Okay, so we need to estimate it using data as well. Okay, so we get the empirical version of this population function. We know that the population function is concave. This in general will not be. So we're going to compute a least concave majorant, and we're going to do it over the transform domain. Okay, so, and I'll show you a picture in just a second. Once we do that, we get again the same string. We're going to bring down that string, get piecewise linear in most cases, and then we take a derivative, and that gets us a step function. Okay, and that now with a revertal back to the original domain, we have to undo the domain transformation, gets us back at a natural estimator for the underlying function little theta. Okay, so I'm going to show you what this looks like in pictures, but it's very similar to before. It has this extra step where we're doing a domain transformation. Okay, and again, I'll mention in a second why we even care about a domain transformation. It's not clear now. Okay, so, and in fact, maybe I'm giving away part of the punchline here, one of the punchlines, which is that now this generalized class of procedures, which we call generalized Bernoulli type estimation, because it's very much like Bernoulli type estimation, but it's generalized because we're allowing a domain transformation to be done. Okay, when we consider this broader class of procedures, which is strictly bigger than the previous class that existed in this literature, we now include isotonic regression as one special case. Okay, so this truly does unify isotonic regression, Bernoulli's estimator, and then so many more procedures that were developed over many, many decades. And there's a certain satisfaction from saying, gosh, we don't really need to do this reinventing of the wheel every time. This all falls in a big framework for which we can establish results and just use those general results in whatever situation we're in. We don't have to redo that work every time. Okay, so I'm going to show you that isotonic regression is an example. So this is, again, a mock data set. So pairs AY, the underlying true regression function, linear in this case. So what does the whole procedure look like? Well, I need to specify what domain transformation I'm going to use. In order to get isotonic regression, the specific domain transformation you end up using is the distribution function, the population distribution function of A, of the exposure. The CDF of A is actually the domain transformation. And the natural estimator for that is just the empirical, very simple. Then we can write down what our transform primitive is, the gamma. We can estimate that very easily. There's not even need for fancy machinery for that term. Okay, so then we can start plotting things. So this is a plot of the estimated transform primitive against the original exposure scale. Trust me, you know, that this is what it is. And now I'm going to plot it with respect to the transform domain. Okay, so I'm not, instead of plotting against A, I'm plotting against this phi NA. Domain transformation is applied. And you can see it's the same curve. It's just that now the spacing between the length of the plateaus has been changed. Okay. Okay, now I'm going to pick out some specific corners on this curve. There's a reason why I'm picking out these ones. So it's a bit gory to go through it. It uses the fact that you have right continuous estimators. So details again don't really matter, but I'm picking out the corners, keeping only the corners right here. And now I'm ready to take my string, come from above, deposit on top of these points to get my least concave measurement. Okay, that's what I get right here, the blue curve. And now I'm going to compute the derivative of these segments to get a step function. And so I get this right here. And so this is plotting the estimate theta n of A, an estimate of what we care about, theta A, against the domain transformation, the transform domain. So we're still not done. We need to now go back to the original domain, which is again just the rescaling of the x-axis here, or the a-axis. So this is what we end up getting. And if you were to just run the pool adjacent violator algorithm, you would get exactly the same. Okay, so it's just an alternative way of doing what had been done in the 50s, but now as part of a template, a recipe that includes so many more things. Okay. Okay, so what about inference? So now I told you we have a generalized procedure that we call generalized Grenander type estimation that includes many things that have existed before. Do we have general theory? And yes, we have general theory. And if you're interested in these kinds of things, and if you're not, it's fine. It's not for everyone. It's quite gory. And so in that paper, we truly have, and Ali, we were asking about different regimes. We have all of that in there. I'm just showing you the simplest kind of result we have, okay? Simplest distributional result, which is reminiscent of what I've shown you before. And that's why there's a general story here. So under some conditions, we end up getting, again, cube root convergence, root n to the 1/3 times the estimation error, stabilizes to a nice non-degenerate distribution that is a scale turnout. And we can characterize that scale factor. The C, we can actually write down what it is. It often involves, it always involves ugly things, okay, that are unfortunate to estimate. And that's the whole direction of research on trying to tackle that problem. But at least in principle, you can estimate that C. And using the work that others have done to characterize the quantiles of the standard turnout, you can construct confidence intervals in the same way you would do it for something that has an asymptotic normal, like a walled construction, wall type construction. You can do that, okay? That's what we generally do. Now you might say, well, you just told me that C is ugly. It truly is ugly. It's so ugly, I'm not showing it to you. And so you might say, well, maybe there's an alternative. Maybe I can do the bootstrap. Bootstrap is convenient. We love the bootstrap. Well, you have to be a bit careful with the bootstrap. Okay? This is one of those classic examples where the bootstrap fails, at least the standard non-canonical bootstrap fails. Okay? It will not give you valid inference. And there's been work on trying to salvage the bootstrap. And so Matthias Cataneo and colleagues did some nice work on using a bootstrap-like sort of bootstrap-assisted approach that does work and is able to do even fancier things like adapting to degrees of flatness. And I think it's still a very active area of research of figuring out exactly how do we do this in practice without having to estimate all these ugly nuisances that appear in there. And this is, by the way, this result here is for 1t at a time. Getting uniform results, okay, convergence as a process, that is, very difficult. This is an irregular problem, and so we don't have access to weak limits, tight weak limits, and so uniform inference is a very challenging problem in this whole area. So I'll just stick to that for now. Okay, so highlights of this procedure as a whole, just to summarize. So it is a general inferential framework that tells you how you might proceed for estimating a given monotone function. It has this nice feature that it unifies a lot of the existing procedures that were derived case by case in the literature. But to me, what's even more interesting, I mean, that's cute, but what's more important is that it gives me a really useful framework that I can use in new problems, new challenging modern problems. I can follow that template to construct and not have to think from scratch. Now, the domain transformation is critical to be able to unify the literature. So that is one reason why you might care. But actually, the domain transformation can do more for you. Okay, so a judicious choice of a domain transformation can make the estimation problem, because as part of this procedure, you have to estimate the transform primitive and so on. So that could be a relatively hard problem. Even though we have templates, it can involve really nasty nuisances. And by smart choices for the domain transformation, you can sometimes get rid of some of these ugly nuisances or make them slightly less ugly. Okay, so I'll stick to that for now, but it can actually help you in the pursuit of the strategy, of the implementation of the strategy, to have a smart domain transformation. As with isotonic regression or Grenander's estimator, there's no tuning parameter involved here. So that's still, at least in the meta procedure. We have large sample theory that describes how this thing behaves. And this is, as I've said before, most useful when you are in a situation where you can estimate the primitive, the transform primitive, and the domain transformation function really well at root and rate. Okay, so because then we can actually simplify a lot of the conditions that we have and a lot of the statements of what the distributional limit is in these cases. We can actually simplify that a lot. And so it makes it actually very doable in practice. Okay, so an important application of this general framework is another paper from Ted's dissertation, which is something we call causal isotonic regression. So remember, isotonic regression was about estimating the mean of y given a under this monotonicity constraint. Now you might say, okay, well, I have an exposure A and I'm learning the relationship between y and a, but maybe I know that there's confounding between y and a. And so that univariate regression may not be very informative. It might reflect the confounding more so than an actual real causal relationship. And maybe I have these covariates W that I think are the potential confounders, so I might want to account for them, okay? So in the process of doing that, I might instead consider this kind of object. So what is this? It's saying, I want to take the mean of the outcome, not just conditioning on A, but also W, because I want to adjust for W. And then I'm going to marginalize over the distribution of W. Okay, so this is, in EPI, they call this regression standardization. In causal inference, they call this the G computation formula, okay, for the single time point problem. So, and you can show that under some causal conditions, this actually is the same as the mean counterfactual outcome, where you imagine intervening and setting the exposure level to be a little a. Okay, so it gives you a causal dose response curve under some conditions. So that's why you might care about this particular curve. And you might know that that curve should be monotone. Okay, and you want to leverage that. So how would you do this? And this is something that was not done. And so we did in this particular paper and with Ted and with Peter. Peter was here as well. So, and what I want to note here is that just remember this expression right here. Okay, I'm saying it comes naturally from causal inference, but it actually appears even in work that has nothing to do with causality. And in fact, in the application, I'll show you in just a second, this exact quantity right here pops up in unexpected ways. Okay, so that has nothing to do with causality. Okay, so we might want to estimate this particular curve under a monotonicity constraint, and this is the kind of stuff that we've done in trying to understand how immunological biomarkers related to the risk of infection or the risk of disease in a certain time frame. We've used this kind of methodology in analyzing vaccine trials. What does the procedure look like? Again, the details won't be important, so you can turn off your brain for a second. If I want to build a procedure here, I'm going to use this generalized Grenander type sort of algorithm. I need to specify the domain transformation. The one we used is the marginal distribution of the exposure A. You can come up with something else, right? Maybe you can find something else that actually has even nicer properties than what we did, right? This is just one choice. And then that helps us to define the primitive. And now I can go and use whatever toolkit I have to build estimators for these quantities. And then I have a well-defined procedure, okay? And I'm showing you here a particular estimator that we have for this primitive. Again, the details don't matter, but this is where you are now using debiased machine learning. So influence function-based debiasing techniques are used here to get a really good estimator of gamma. If that doesn't make any sense to you, that's fine. You would learn this in the second year. So, and this procedure involves some nuisances, things like the conditional mean function, a ratio of densities, ugly nuisances, unfortunately, that have to be estimated as intermediate steps. And this procedure right here, which is Ted's paper, has been extended to be able to deal with outcomes that are right-censored, with exposures, that are actually missing, because this happens in the context of our vaccine trials. So we need to have these generalizations to be able to use these techniques. So we've had to do that, but again, we have the template. We just use a template. We don't need to reinvent the wheel. We just need to crack the template. The screen just opened. Just gonna make sure that we're still on, because there's something weird going on. Okay, I think we're good. Okay, so so that's that. So now I want to tell you about an application, and this is absolutely sincerely not just methods looking for an application. This fell on our lap, and it was quite interesting the way it happened. And so this really emerges out of a collaboration I've had for many years now with Helen Chu. Helen is an infectious disease doctor, professor here at School of Medicine and School of Public Health. In fact, she's now Associate Dean for Research in the School of Public Health. And Helen is a preeminent researcher in infectious disease and viral respiratory pathogens. In fact, perhaps you've heard about her because she was the first US scientist that detected community transmission of SARS-CoV-2. Early in the pandemic, the first case was in Seattle. And there's a fascinating story on how she used an existing study and banked samples and rebuffed the FDA that told her, you cannot look at your samples, you're not allowed to do that. For the sake of public health, she did that and was able to find that, oh God, there's already transmission going on, right? And so that was really important for organizing the public health efforts here in King County. So there's a nice New York Times article about her that tells the story, so you can look it up. So Helen has been running these really fascinating studies of viral surveillance in the community here in the Puget Sound area. So the earlier one was the Seattle flu study. Then the pandemic hit. And so she set up the Seattle Coronavirus Assessment Network, a testing program where you can basically go online and say, I feel sick, I'd like to test myself. And they would send you a kit. You'd swab yourself, send it back, and get results really quick. Really cool. I used it many times. What I'm going to actually talk about today is not that, it's this Husky coronavirus testing, okay, which is a program that was set up here at UW for providing COVID testing for everyone on campus, okay? And so this, of course, is at a time when testing was difficult to find. So this started in September of 2020 and went until mid-2023. 40,000 participants, the entire UW community, so faculty, staff, students, and more than 230,000 swabs processed. A lot of swabbing happened in this study, okay? And many studies have come after that. I didn't list all the amazing studies that Helen has been doing. This is just, I stopped where this analysis comes in. Okay, so this particular testing program was a service to the community on one hand, but it was also an opportunity to learn about this new pathogen, right? And so the data from this program has been used to answer many interesting questions. The one I want to focus on today is a question about symptom persistence, or long COVID, the epidemiology of long COVID, okay? And tackling one particular question of that based on a sub-study of the HCT program. So let me tell you a bit about this sub-study, which I'll call the long COVID sub-study. And the work I'm talking about now was actually led by a former PhD student, Charlie Wallach, who worked with me, myself, and Noah Simon. He's now faculty at the University of Rochester. And so he led all this work. So we worked together with Helen to do this. So what was this sub-study about? So basically in March of 2022, this study was initiated. The sub-study was initiated. And what they did is for individuals who tested positive as part of the Husky testing program for the first time between December of 2021 and July of 2022, and keep in mind, this was the window within which we had that huge Omicron wave, the first Omicron wave, okay, where most people got infected. And so if you tested positive for the first time during this window, then at least 28 days after your positive test, you would get a ping to fill out a survey, and the survey would ask you about your symptoms. Do you still have symptoms? Yes or no? That's the information you get back, okay? And I'll show you a little schematic to help you understand the data structure because it's really important. And the point here is to be able to understand symptom persistence. Okay, so how would we put this down mathematically or statistically? Well, we can define for each individual a time t, which is duration of symptoms, from positive test until resolution of symptom, that's t. And I really wish I could observe t for a bunch of people. Then I could say something about the distribution of t. In this study, it's going to turn out that we're not going to see t for anyone. Okay, so it's a really complicated sampling framework that makes it interesting for us statisticians. So what I actually get to see in this study is, well, people get pinged to fill a survey. They fill a survey at some point. I get to know when they fill the survey. So I know how much time has elapsed between their positive and when they respond to the survey. So that's M. That's what we call M. M for monitoring time. It's the survey response time. If they never respond, at some point I cut them off. I say, okay, you're a non-responder at the survey. Okay. Delta is sort of the outcome that I get to collect here. So if they respond, they get to tell me, I have had resolution of symptoms. I'm fine now. Okay, so delta 1 tells me I don't have symptoms anymore. Delta 0 says they're still going on. Okay, I see this binary. And then I also get to see covariates, W, on everyone at the time of testing. When they come in for testing, we get a bunch of information on it. And our goal here is to learn the distribution of T, but we do not get to see T on anyone, not a single person. It's not like right censoring, where some people you get to see T, some people you don't. Here, we don't see T for anyone, okay? What we actually get to see, in addition to covariates, is the pair M and delta. When did you respond, if you responded, and what did you respond? Did you say that you had resolution, yes or no? Those are the data, okay? And this, it's easy to fall into a trap of saying, okay, well, I have binary outcomes, so I'm gonna do some kind of logistic regression, okay? And so that's the easy trap you can fall in, and it gives you meaningless results. Because delta is yes or no at a random time, a different time for different people, right? People are responding at different times. So how the hell do we proceed? And for those of you who've done survival analysis, this is an example of current status data. Current status data, which I had learned about as an undergrad, and it was cool, it was interesting, it was weird, it was hard. And never did I ever stumble on current status sampling in real life. This was my first case, in the last year or 2 years. I was really excited about that. And so this is an example of current status data, which is known to be an extreme form of interval censoring. So it's really, oops, screw it. We'll be back. Okay, so it's an extreme form of interval censoring where you really have a lot of loss of information there. And so it turns everything into a difficult problem. In fact, this is a case where even just estimating the distribution, the function of T, is actually not a root n problem. Okay, so it is a local parameter, even though it doesn't look like it, it's just the distribution function. Well, it depends what data you have, right? Okay, so this is now just a schematic to show you an example of data that could come in here. So we have 7 participants here. The plus here is telling you when they get their positive test, okay? This vertical line right here is when the study was actually initiated in March of 2022. Individuals that have had at least 28 days since their positive test, so these individuals right here, they've all had 28 days, that's the blue bar. They get the ping exactly in March of 2022 because it's been 28 days. I can contact them. I don't want to contact people too early because I want to know about what happens in the longer term, right? So these individuals get pinged, so these are the little gray S's, to answer a survey. The other people, they get the ping as soon as they get to the 28-day mark. Okay, so you see this person here, that's the 28-day mark, they got their ping, and same for those people that got positive test, respectively, from that point on. Now, when do they respond? Well, it depends on them, right? And so that's random. And so here, this person right here responded pretty quickly. Okay, so the green S right here is when they responded. The color means something. Green says, all good, I don't have symptoms anymore. Okay, that's the information they're giving us. This person right here took much longer to respond, but they respond eventually, and they told us, I still have symptoms. This is orange. And some people never responded. So this is an example of a person that at some point is deemed to be a non-responder based on the length of time that's elapsed, okay? So now if we just take a few of these examples, what does this all mean in terms of the underlying T that we wish we had been able to collect, but we didn't? So for this individual who responded right here at this time, we know how long has elapsed since their positive test, that's M, and they tell us delta is 1. I've had resolution. So what do we know about their T? Their T is smaller than their M. That's what I know about T. That's why it's a form of interval censoring. I know that T lies in the interval 0, M1, their T1. For this person right here, who responded after their M5 period, they said, no, I haven't had a resolution yet. So the resolution happens sometime in the future. So for them, T5, is bigger than M5. So it lies in the interval M5 to infinity. That's what we know. That's the information we have. And then here's the example of a person who didn't respond. So at some fixed period is deemed to be a non-responder. Okay, so how do we proceed now? Hopefully data are clear. Now, how do we, and what the hell does this have to do with monotone functions? Right? A natural question to ask at this point. Seems to be a huge divergence, a huge tangent that we've taken. It comes together right now, okay? So our goal, remember, is to estimate the distribution of T, CDF of T. That's really what I wish to learn. In order to be able to proceed with these kind of data, we need to make some assumptions. We don't get anything for free here. So let's say we're focusing on trying to estimate the symptom resolution probability at time little t, for a little t that is something we think we can learn about, something within the window of times we'll get to see. We don't see anyone before 28. And in our analyses, we said, you know what, if it's been 120 days, it's a long time, we're going to consider you a non-responder because in that period, you may have gotten infected a second time. And now I don't know if what you're going to tell me has to do with the first infection or second. So that's when we cut things off. So if we stay within that interval, then perhaps we can make some progress. So this is what we're trying to learn. How do we make progress? Well, we have to make some assumptions. If we're willing to assume that the response time, the survey response time, is entirely uninformative, it has nothing to do with the resolution time, strong assumption. If we're willing to make that assumption, then we can easily show that this symptom resolution probability is none other than the mean value of the indicator delta conditioning on M equals T. Okay, so easy to show. Under the strong assumption, this is the case. And so we've now boiled down the problem as one of estimating a univariate regression function. The mean of delta given M. Delta is the outcome now, and M is a univariate regression, regressor, covariate. So univariate regression problem, we know how to do that. And by the way, this is equal to the symptom resolution probability, which is a monotone function. We know it's a CDF. So that is telling us that this regression function must be monotone. Okay, so we're back in the world that we were living in just some moments ago, okay? Estimating a univariate regression function under a monotonistic constraint. We know how to do that, isotonic regression. We've known since the 50s, okay, how to do that. We can do that. Now you might say, well, this is crazy, assuming this independence. That's nuts, right? And I say, yes, it is nuts. Okay, so we have covariates that we've recorded on people. Maybe we're willing to assume that there may be some dependence between the response time and the resolution time, but we want to say that conditioning on the covariates, that is explained away, that we're able to explain away any informativeness, okay? If we're willing to make that different assumption, leveraging the covariates we have, then we can show that this symptom resolution probability can be expressed as this little beast right here, which I told you to remember an expression from before in causal isotonic regression. If you remember, the expression we had was exactly this right here, but delta was Y and M was A. Okay, that's exactly the same expression we had. It's just a regression standardization. Okay, so that's exactly the same and we know that this has to be monotone because it's a CDF. And so we are back squarely in the setting of causal isotonic regression, even though this has nothing to do with causality. Okay, and we can proceed. And in fact, this is what we ended up doing for the analysis. We're on I'm going to be finishing soon. I'll show you the results of the analysis, and then we'll end. So we implemented this causalized static regression to analyze data from this long COVID study. We focused on the period 30 to 90 days with non-response at 120 days. We adjusted for things that we thought mattered that we collected: sex, age, comorbidities, symptoms when you're testing positive, what kind of test did you use, PCR versus rapid test, time since last vaccination, things that we thought could matter, we adjusted for. And nuisance involved, we use machine learning tools. That's not important, but all this supports that. And here is the primary analysis. Okay, so this is based on about 3,500 participants that tested positive during this period, got a ping. How many people actually responded? Those of you who work in surveys will know that response rates are often low, right? And so close to 1,500 responded, which is a small fraction, but it can be worse. It can actually be worse. But the framework allows us to account for that, at least to the extent that's explained by the covariates we get to collect on everyone. We're going to try to compensate for those individuals that we're missing, that don't respond, okay? So the way to read this graph, this is giving you the estimated probability of still having symptoms at a given time, okay? So at 30 days right here, we get about 18%. 18% still having symptoms at 30 days. Keep in mind, this is a mostly young, healthy population of mostly university students that are all vaccinated. 18% is pretty high, but it matches a lot of other studies and study designs that have done this kind of work. At 60 days, you're down to about 13%. At 90 days, 3 months out, it's lower, but it's still around 8% at 90 days. A bit troubling, So anyway, so this is basically what we can get from this kind of analysis. Now, before ending, what I'll say is there's a slide that I'm not going to have the chance to tell you, which is you might say, but this is still crazy. You're still assuming that you can explain away any dependence between the response time and the resolution time based on your baseline covariates. But it's very natural to think that whether or not a person has had resolution of symptoms may themselves change their propensity to answer the survey. And you can argue it either way. It could make them more likely to answer because they think they may have long COVID, they want to participate in research, or maybe they're so sick that they say, screw you, I don't want to deal with your research, right? You can make it either way. So what we did next was to do actually sensitivity analysis, where we embedded various departures from this assumption to see how sensitive our results are to deviations from this assumption. And I'll just show you the last plot. I'll skip the details. They're fascinating, but we don't have time. Quite a bit of this is the primary analysis. And these are the different values you would get if you'd been able to implement this procedure, which requires turning the Carone-Debiased crank to produce new estimators under different levels of departure of that independence, conditional independence. At 30 days, it actually is quite sensitive. But once you get to 90 days, look at this. It's pretty flat. It's almost flat, okay? So that starts to lend credence to these numbers. It says that we actually, this may be real and not just an artifact of the assumptions we've made. Okay, so I'm ending now. So concluding thoughts, we're in. So what I've talked about today is this idea of generalized Carone-Debiased type estimation, which is a general procedure or class of procedures, a template that can be applied to do non-parametric inference on monitoring functions, mostly useful for cases where the curve of interest is local, not root n-estimable, but the primitive is global, sorry. It allows you to integrate into all of this machine learning and device machine learning tools. Practical challenge, I'll leave that for now, and I'll end with one slide, which is that there's a lot of interesting work still being done. I'm biased, of course. I think the work is interesting. Hopefully you agree. But there's a lot of open questions in this area. Some that I'm doing with former students, but here I'm featuring current students who are actually working on related questions. In an alternate universe, I would speak, I'd be more efficient in delivering talks and I'll be able to tell you about some of that work. I'll let the students do that for you if you're interested. But these are examples of students who, Charlotte, Grant, Kat, Lars, and Nolan, who are working on problems related to this monotone function problem. If you're interested in this area, it's an area that spans many decades. It's difficult. It's not standard. But there's a beautiful book, actually, that came out about 10 years ago. So it's a great starting point if you're interested in learning about this. Okay, I've overstayed my welcome. And so references, if you're interested, I can share these slides with you and we have these references. So that's all.
A question from visitors.
Putting people on the spot like this?
We can always,
Good for you.
Portrait Marco for the people who are already here in the kitchen area right after. But the computer students have a curiosity, perplexity, application. Yeah.
Sorry, I have a very naive question about vaccines, like the symptom study. So why would like designers question asking
Yeah, that's a good question. So why did they just ask what's going on right now rather than, oh, if you don't have it, how long has it been? You could ask that, certainly, that would be more information, but then you need to deal with potential for recall bias, right? Recalling something that happened in the past is always a bit challenging, right? I agree, it would be strictly more information. Then what you do with that, you could say, okay, it's something, it's a proxy perhaps for when the actual time is. I didn't get to see the actual time, but they're telling me something, and maybe it's closely connected with the potential for recall bias, right? And so it would be more information, and then we can say, okay, let's try to account for that extra information. So I agree, it would be nice to have, and it would change the data structure. Again, you would not get to see the exact T, but you would get to see some kind of proxy for T, right? Their recollection. So it would be a good idea. Yeah. Yeah, and as far as I know, that was not a question that was asked in that particular survey. But this sub-study was done before I was involved in this. So we got this data and said, okay, what do we do with this? This is really challenging. And we have to do this properly, accounting for what actually is in this data set. And it's very limited information, but it still allowed us to make some conclusions that I think, are meaningful. But great point.
Well, with that, I was told pizza is already up in HRC